This plot shows the amount of binding energy per nucleon. A nucleon is either a neutron or a proton. The nucleon number is the sum of the numbers of neutrons plus protons in a nucleus, as a function of the atomic mass number, A. The energy units are MeV, which stands for million electron volts, a standard unit of energy in nuclear physics. So there's A down here, and then here's our binding energy. This curve indicates how stable atomic nuclei are. The higher the curve, the more stable the nucleus. Notice the characteristic shape with a peak near 60, where A equals 60. These nuclei, which are near iron in the periodic table and are called the iron peak nuclei, are the most stable in the universe. The shape of this curve suggests two possibilities for converting significant amounts of mass into energy. The first is fission. From the curve of binding energy, the heaviest nuclei are less stable than the nuclei near A60. So here, down to here. This suggests that energy can be released if energy nuclei split apart into smaller nuclei having masses near A60. This process is called fission. It is the process that powers atomic bombs and nuclear power reactors. Fusion reactions. The curve of binding energy also suggests a second way in which energy could be released in nuclear reactions. The lightest elements, like hydrogen and helium, are down here, have nuclei that are less stable than heavier elements up to A60. Thus, sticking two light nuclei together to form a heavier nucleus can also release energy. This process is called fusion, and is the process that powers hydrogen bombs and, hopefully someday, fusion energy reactors. In both fission and fusion reactions, the total masses after the reaction are less than those before. The missing mass appears as energy, with the amount given by the famous Einstein equation, E equals mc squared.